Hello friends, so the LeetCode problem we are going to solve now is called distinct subsequences. We can see that this one is a LeetCode hard problem and also a very well-liked problem. Now basically we are given two strings s and t in the input. Now we need to return the number of distinct subsequences of s which equals to basically t. So how many different ways we are able to generate string t from the given string s, and that is what we need to return. So let's try to understand it with a couple of examples. Let's say that we are given the string as a b b and the given string is a and b. Now in this case, notice that we can generate t in two distinct ways. First one is if we use just this first to ab, or second one is if we delete this ab and we use the first and last ab. So that is what we need to return as the answer. Second scenario is that let's say if we are given the word rabbit RABBBIT, and in the subsequence that we are trying to generate is RABBIT. So in this case we are dealing with three b's over here, and over here we only need two b's. So basically once again we can generate it using three distinct ways. First way would be where we are eliminating or not considering this b, so that forms rabbit. Second scenario would be where we delete this b, and third scenario where we would not consider this b, and in either case we would be able to generate t, so we can return the answer. Now as always, let's try to understand the brute force solution first. Well, we know that at any given character s, we need to define that will that character help us generate value that is currently present in t. So for a smaller example, let's say the given values a, b, b, the current t that we are trying to generate is a and b. Now notice that at any given location of s, we are making two decisions, whether to include this a or exclude this a in order to generate the t. If the characters match, we include it for our subsequent answer. If they do not match, we could have excluded it and then try to see whether some other sequence makes sense or not. Same way, after doing this, even for the other two characters, we still have the same two possibilities on whether to include this character or not. And very quickly we realize that this leads to basically exponential time complexity, where we are dealing with somewhere between, like, I guess 2 to the power of n time complexity, where n defines all the characters that are currently present inside the given s, and 2 because we are making two decisions at any given interval, which is a very expensive time complexity if you plan to solve this. So we'll have to find a better way to compute. Now just try to understand that the optimal approach in this case is going to involve the most beautiful approach in the entire computer science, and that is going to be dynamic programming. But the thing is, let's first understand that why do we need to use dynamic programming in this case. Well, because all the values that we have currently calculated so far are going to help us make future decisions. Let me give you an example. Let's say the given values are a, b, b, c, and the value we are trying to generate is going to be a, b, and c. Now notice in this case, if we have already computed that in order to generate this character a, there is only one way we could do it, why don't we just keep that information handy? So next time when we encounter a character ab, we don't have to look the entire ways to generate ab from the given input. We already know for a fact that this are, like, let's say there is only one way to generate a, we know for a fact, and then we found like 2 or 3 occurrences of b. Then in either case, for each of the occurrence, we can recompute that result. So let's say that since we are given 3 b's over here, we know for a fact that there are going to be 3 distinct ways for us to generate a, b, no matter what. And now when we are dealing with c and we realize that there is only one c over here, which means there is only one way we could do it, which means it does not add to us being able to generate this value. So overall the answer is going to be 3. But let's say over here, if we are also dealing with 2 c's and a d, then also the answer might change. So at any given instance in the character that is currently present at t, we define that whether that character matches the subsequent character inside the s or not, and based on that we are trying to check that what has been the previously calculated results for each one of the characters, and then we are able to make that decision on whether to include that character or not. Now notice in this case, the number of subsequences only increase when the characters match, and basically when we have already calculated all the values that we have calculated so far. Because over here, if this was ABC and ABC, we know that there is only one distinct character. But if this was ABBC, then we have a match at B and one time and a match at B at the another time. So basically we can take whichever B path we want and the answer would still yield the same result. So that's why we are dealing with two possibilities over here. First possibility is if there is a match. If there is a match, basically we include both the possibilities of calculating or both the paths that would yield us in a subsequent. If they do not match, then we simply do not need to include that, and we can keep the same subsequence number that we have even if we did not included that character from the given subsequent s, because it wouldn't change the total number of result that we are trying to generate. And we would understand this if when we start using a DP matrix in order to solve this problem. Now the question becomes, why do we need to use a DP matrix? Because the characters present in S and the characters present in T, they both are of value to us, and we will have to calculate for every single possible permutation combination. And in the very last result that we find in the matrix, that is going to be the total number of distinct subsequences we can make. So I have currently drawn a big matrix like this. Now notice that all the characters we have in the T are currently present over here, and all the characters in S are currently present over here as part of this. So this is going to be basically our jth value, and this is going to be basically our ith value. Now we know that this is going to be a dynamic programming solution. Also, for any DP solution, we need two things. We need a base case. So base case is going to be quite straightforward. It would be as if the given S is not present, or if the given T is not present, what is going to be the value? We know that if, let's say, that T is not going to be present, which means there is only way for us to generate T from the given S is not to include any characters, because that is also a subsequence of given S. So all of these numbers would only mean value number 1. So we can just mark them as 1, because if the character in S is present but subsequent T is not present, we can only make one subsequence out of it. Let's understand vice versa. If the given S is equal to null, but we still have some value present inside the given T, which means we would never be able to generate T based on the given S, because the given S is empty. So because that is the case, then all of this results are going to be 0, because we are not able to generate T, or we are not there does not exist any subsequence that would be able to form T from the given S. Okay, now we know that what needs to be the recurrence relation. So recurrence relation is going to be quite straightforward. For any particular ith and jth value we are trying to calculate, we would see that if they match or not. If they basically match, we will have to do the sum of both the subsequence, which means we would need to consider that what does the diagonal value for any particular character is. So that is going to be, let's say for I and j, if they match, then the diagonal would be I minus 1 and j minus 1 plus what the previous subsequence has been with respect to s, and that would be the value I minus 1 and the current jth value. We'll have to do the sum of both of these two characters. So let's say that for an example, we notice that this A matches this particular A. So because this cell has a match, then we'll need to combine the subsequence we are able to generate over here plus the subsequence that we have been able to generate over here, because we can take both the paths from here. And notice that only the values of I differ, j would remain constant, because we are trying to build T from the given S. Now I know it sounds confusing, but we'll understand it when we move to building our matrix. Now the second scenario is that if they do not match, then simply that does not add any value for us to build a subsequence. Let's say over here, this A and this B do not match. So because they do not match, they are going to have the same number of distinct subsequence value that we calculated even for the previous result of I. That is going to be the cell above it. So we'll just replicate that value. So if they do not match, basically we will just take whatever the value of I minus 1 and j was as it is, and we will store that in the result. So now based on this to recurrence relation, let's see that what does our distinct subsequence that we are able to find. We notice that there is a match over here, R and R, they do match. So because they do match, we are going to take the sum of the diagonal value and the top value. Now notice diagonal is also going to be 0 for the first value, so we'll just mark it as 0, and sum of this two is going to be 1, so we'll mark it as 1. Same way for this R and A do not match. Because they do not match, we are going to carry forward the value from the top, so this would become 0. Same way R and B do not match, so this would become 0. R and B do not match, so on and so forth. So all of this are going to be 0. Okay, now A and R, once again they do not match, so we will take the value from the top. Now over here in this case, A and A actually match. So for this cell, because they match, we are going to do the sum of this character plus sum of this character. So let's just mark these value as 1 as well. Once again, A and B do not match, so this is going to be value from top, and so on and so forth. We will just mark all of these values as 0. Now for B and R, they do not match. So because they do not match, value from the top 1. B and A do not match, so once again value from the top as 1. B and B do match, so because they do match, we are going to do sum of these two values, so the answer is going to be 1. Okay, once again B and B once again match, so sum of these two are going to be 0, and once again B and B do match, so sum of these two are still going to be sorry, once again B and I do not match, so value from the top, and then B and T do not match, so value from the top. Now B, once again, so this is going to be value 1 1 so far, but now this, notice that this B also matches this B, so in this case we are going to do sum, so this would become value 2. Now once again this B also matches this B, so once again the sum is going to be value number 1, and now so on and so forth. These are going to be 0 0 as it is. Now for this third B, once again this is going to be 1, this is going to be 1. There is a match with this B, so because there is a match, I'm going to do sum of previous two elements, so this is going to be 3. Once again for the subsequent B, once again there is the sum, so this is going to be 3. So I'll add those values, and now this value is I, so they do not match, so value from the top is 0, and once again T do not match, so value from the top 0. Okay, now I'll change colors again, so better visibility. For I, basically all of these values do not match, so up until that point we can just carry whatever value we had from the top, but now this I matches this I, so we are going to do sum of these two values, so total is going to be 3. Once again this T do not match this I, so once again the total is going to be 0. And lastly for this T, last time we are changing the colors, and basically the value is going to be same that we have been able to identify all up to this, but this last T matches this last T, so basically the sum is going to be these two, and the answer is going to be 3, and this is what we need to return as the answer. So basically you understand that how using dynamic programming we were able to shrink our solution from 2 to the power of n to basically time complexity of big O of m multiplied by n, where m is the length of s and n is the length of t, so which is a very good time and space complexity. We cannot go any more optimal than this. Now in terms of space complexity, because we are using an extra matrix, this is also going to be big O of m multiplied by n, that is a reasonable cost to pay. So now let's understand the coding solution for this. The coding solution is going to be quite straightforward. First, we are going to define two variables m and n to take care of the length of the given subsequent s and t strings. Then we are going to initialize a 2D dynamic programming array, and basically we are taking it as m plus 1 and n plus 1. This is to take care of the base case. Okay, after that we will initialize for basically when the given I and I is equal to 1 and j is equal to basically 0. So for the first column, all of those values are going to be 1, and all the jth column is going to be 0. We haven't mentioned it over here, but that would be like an intuitive thought that we can understand. Now we'll start filling in the dynamic programming array. We will check that for the given dynamic programming array, If the characters match, then we are taking in the value from the diagonal and the value from the top and summing it up. That is going to be our subsequences. If they do not match, we'll just directly inherit the value from the top of the DP matrix that we have calculated so far. In the end, we will simply return the result or the very last cell in the DP matrix. Coding is not that much, but concept is quite important. Let's try to run this code. Okay, seems like our solution is working beautifully. Let's submit this code. And our code beats nearly 65% of all the other solutions, which is pretty awesome. In terms of space complexity, we could have done things slightly better, but anyways, this is also a reasonably good space complexity. Once again, the coding solution is present in our GitHub repository, so feel free to go and check it out from there. Thank you.